So before I get started, I want to let you know that all of the slides and the little bit of code we'll go through today are available at this bit.ly link. And that link is going to persist at the top right corner of the slides today. So you do not need to download it right away, but whenever it's convenient for you, it will be there waiting for you. And what you'll have is a PDF of what we're going over, which can save you some time if you're planning to take notes or whatnot. As Roger said, this is going to be the first in a three-part series about how to build Shiny apps. Originally, we were going to do it all at once, but it quickly became apparent that it'd be much more helpful if we split it up and spend a little more time on each of the subjects. What you're going to learn today is how to build a basic Shiny app. You'll learn to make the parts of the app reactive, and you'll also learn how to deploy and share your app afterwards. Leaving here today, you'll be a beginning Shiny developer. You could make your own apps, but the apps, to be honest, they won't be very thrilling. They won't look that pretty. And even though they do incredibly useful things, what they do in terms of Shiny will be fairly simple. If you come back and join me next week on May 27th, it's a week from today at the same time, we'll look at how to customize the reactions in your apps. So we'll build upon what we learned today, and you'll learn some patterns for making useful interactions for your users to use, such as delaying reactions, using buttons, that sort of thing. A week after that, we'll come back and look at the appearance of your app, how to lay out the elements of your app, and how to shape the way they look. This is purely cosmetic, but it's the sort of things that make your app look truly attractive. I'm going to assume that everyone here has seen a Shiny app or knows what a Shiny app is. We will look at some, but the apps we're going to look at today are very simple. If you want a better idea of what Shiny can do, I recommend that you visit this website, the Shiny Showcase. Here I've put together a variety of apps that have been contributed by people who work in different industries, different businesses, that sort of demonstrate what other people are using Shiny to do. And many of these apps are quite impressive, and they could be a good source of motivation as well as ideas. The other prerequisite or background knowledge I'm going to assume you have is that you know how to use the R language. So a Shiny app is basically a delivery vehicle for an R script. You write an R script, which is a program written with R that does some certain thing. And all the Shiny app does is allow you to make the function of that script available to people who don't know R. You could put it in your app, you could put the app online. People could do the analysis that your R script does without needing to write anything, without needing to do anything really other than click a website. But for you as the developer to make this app, you will need to know how to write the R scripts you have in mind. Obviously, we're not going to learn how to use R in the next 40 minutes, but I'll give you some resources for that. RStudio has actually done a lot of work to make it easier to use R. We've written some books that can get you started. We've made some videos in collaboration with O'Reilly if you prefer to learn through videos. And we've also helped make some interactive tutorials if that's how you prefer to learn through DataCamp. Then at the bottom of this web page here, bottom of the slide, is a web page where I've put together tips that I think would be helpful for someone who's willing to use the internet to learn how to use R with free resources. You'll just have to do a little more work since all these things that I've put together here at this website are free. They're not as polished as the other materials. But if you need to brush up on R, you can start with any of these resources. Let's assume that you know R, and now you want to build Shiny apps. The first thing that I recommend you do is understand the architecture of a Shiny app. And to do that, we'll look at a real Shiny app. So if I leave the slides for a second, come over here. This is a Shiny app. It's a fairly simple app. You may have seen it before. It's an oldie, but a goodie. And what you'll notice is this app is a web page. So this is just Google Chrome that I have open here. Inside the app, there are components built with R. So this plot over here is made with R by calling the plot command. The plot shows data that comes from R. It's the Iris dataset, canonical dataset for doing cluster algorithms. And the data in this plot is colored based on a k-means clustering algorithm that R itself implemented. You'll also notice that parts of this website are manipulable. I could open up drop-down menus over here to select different variables to plot, and when I do, the app automatically gives me a new plot generated with R that shows the new variables I selected. And I could also use this numeric input to change the number of clusters I want the k-means algorithm to find. Behind this web page, there's a computer serving the web page. And this computer is running R, has an open R session, and it's just waiting for me to interact with the app. Whenever I make some change to the app, the computer reruns some R code to build a new plot, and it sends the plot to the web page. So think of this web page as the tip of the iceberg. Behind this web page, there's another component to the Shiny app that I can't see, and that's a computer running an R script that the Shiny developer wrote. To put this visually, every Shiny app looks like this. There's a web page that the user visits, and there's a computer that serves that web page by running R. Today, the computer that's serving my Shiny apps is just my laptop. And when you make a Shiny app on your computer, it's just going to be your computer that serves the Shiny app. You might see the Shiny app in your web browser, but it's not coming there from the internet. It's just coming straight from your computer. If you wanted to share the app over the cloud, all you have to do is arrange to have some type of web server service the app. So you set up the web server to run R, to maintain the app, and then anyone can access the app through the cloud because the web server is already designed to talk to the cloud. So what does this mean for you as a Shiny developer? Well, when you make a Shiny app, you'll need to make two components for each app. First, you'll need to make some sort of user interface. This will be a web page that the people who visit your app will see. The user interface will really just be a web document written in HTML, but you don't need to know any HTML. We're going to generate that document from R. The second component of your app will be a set of instructions written in R for the server to follow. These instructions will tell the server what to do when your user changes the different input objects in the app. The instructions will leave the server in such a place that it can handle everything that might happen, and you can go away. You don't have to watch as people use your app. If we take a look at our app, this app over here, I could show you the R code I used to make it. It's all right here. If you downloaded that bit.ly link before and unzip the file, you'll notice that you have these files in your folder. First is the slides for today, and the second says code. And this app is just the code that appears here in app.r. I have it open right here. You'll see that the code has a UI component. All this being saved to UI is building that web document that the app lives in. If I copy this and paste it into the command line, hit enter, you'll see that all it's generating is a bunch of HTML. This is the HTML web page that the R components of our app will live in. Let's go back to our code over here. Next, you'll see it defines a function for the server. This function contains the instructions that the app needed to build that plot and do the clustering. And then finally, this code over here knits the UI component and the server component together using Shiny app. Now that you know the architecture of a Shiny app, it's time to start building Shiny apps. And when you do this, I recommend that you start every Shiny app, whether it's your first or your 100th, with the same template. Use this template until you have a reason not to. This is what the template looks like. It's 3 lines of code if you don't count library Shiny. First line of code sets up a UI object, the second a server object, and the last one's knit the two together into a Shiny app. You can memorize this code. I think you'll end up memorizing it anyways through repetition as you build apps. But for today, you don't have to. I've included it in the code I sent you. It is the o1 template.r file. And if we open that file, you'll see those lines of code there. To use this template to make an app, all you have to do is copy it and paste it into the command line. When you hit enter, RStudio will launch an app. This is the Shiny app the template makes. It's an empty Shiny app, just a blank page. It's really pretty simple, but it's also very profound. There's nothing in this app, including error messages. So we know that the template works, and it's a safe foundation to build your app into. You could use the template to add things to your app. So you start with the template. If you want to add something to your app, the way you do that is you just add it inside a fluid page in the template. So we could put a piece of text into our app. Copy that to run in a second. Go down here. We'll notice that we don't have a command line to run anything in. And this is just an important little tangent about Shiny apps. Remember, there's a computer that's maintaining the app in the background, and today that computer is going to be your computer. And that computer is using an R session to maintain the app, and today that R session is going to be your R session. So we notice this app is still up. It's just a blank app. And while it's up, our R session is going to be busy maintaining that web page. If we want to do something else in R, we'll have to close the app by clicking the stop button right here. When I click stop, we'll see that the app went gray. That means it's dead, basically. Now I have the command line. So now I'm going to copy and paste the template with my hello world in it. Run that, launches a new app, and you see that it put hello world into our app. Well, obviously we want to put more in hello world in our app, so let's take a look at how we should go about building out our app. You've seen the stop signs that stop our apps, and this is the code I just ran. As you build your Shiny apps, I urge you to think in terms of inputs and outputs. Inputs are things that your user can toggle or use to provide values to your app. In our app, we have 3 inputs, 3 drop-down menus that the user can use to select variables and the number of clusters. And then outputs would be the R objects that your user sees. These could be plots, tables, text. They're the things that will respond when your user changes an input. And the way you add them to your app is very simple. In both cases, you just add inputs and outputs to the Fluid Page section of the template. Anything you put inside Fluid Page is going to end up in your app, and inputs and outputs are the things we want to end up in our app. You add inputs with input functions, and you add outputs with output functions. So it's fairly simple. All the things we're going to go over today, by the way, are just the ground rules for using Shiny. When it comes to Shiny, I think these are probably the most ephemeral part of learning Shiny, because this is the part of Shiny this is just the way it is. After today, the things we learn will make more sense because they're built upon other things, but for the moment, this is just the way it is. Let's look at how to add input functions. What you see up here is an input function that would build a slider object in Shiny. If you ran this code at the command line, this is what you'd see back, a piece of HTML that's associated with some CSS classes. And when you put this into your template, this is what it adds to your Shiny web page. So if you take your template and you add the slider input function to Fluid Page, it will build the app you see over here on the right. Now this is just a slide, so I can't actually move that slider for you, but if I ran this in R and launched the app, you'd see that you can manipulate that slider and change its value. Altogether, Shiny provides about a dozen input functions that you could use in your apps. These all come with the Shiny library, and you'll see that most of them end with the word input, which is why I call them input functions. Among these functions, you have options to place buttons in your app, checkboxes, radio buttons, drop-down menus, sliders, and then specialized fields for dates, date ranges, numbers, passwords, and text. All in all, basically every sort of interaction that a user can make with a mouse click on a web page is included in one of these inputs. Each of the input functions take the same basic syntax. They all begin by taking an argument called input ID. That argument allows you to assign a name to the input. You can give the input any name you want, but every input in your app should have its own unique name because you'll use it later to identify the input. One thing to notice is that this argument name has a lowercase d on the end, which can be a bit tricky at first. The second argument that every input function takes is a label argument. When users see your input object like a slider or a button, they won't necessarily know what the slider controls or what to do with it. So a label provides a way for you to explain that. The labels will appear in an intelligent place near the input object. For a slider object, it'll be right above the slider. If you don't want to include a label with your input, just put 2 quotation marks. That'd be an empty character string. And then finally, each input object takes additional arguments that help that input object do its job. For example, a slider input object needs to know a minimum value, a maximum value, and a starting value for the slider, but that doesn't make sense for action buttons and so on. If you want to know what specific arguments to use with a specific input object, you could just look at the help page for that input object. The way you find a help page in R is by typing question mark in front of the name of the function you want to look up. So question mark slider input would open the help page for slider input, and that would explain all the different options for arguments you could pass to slider input. Now let's look at outputs. These are things like plots, tables, text, the things you make with R. Shiny provides a second family of functions, which I call output functions because they all end in output, that place into your app different types of output. So there's a dedicated output function that places plots in your app, a dedicated function that places tables, one that places text, and so on. Here's the complete list of output functions. The syntax for the output functions is somewhat similar to input functions. First, you'll notice at the beginning of the function name for output is the type of output you actually want to place into your app. And then each output function takes one argument, one required argument called output ID. And just like with the input functions, this is a name to use for the output. You could pass any name you want here, but again, I would recommend that each output object has its own unique name to avoid errors. So if we add an output function to our app, we pass it to Fluid Page as a second argument. Don't forget to put a comma between the arguments of Fluid Page. And then when we run this app in R, this is what we'll see. Ta-da. So it doesn't look very different, which might be a little disappointing at first, but if we looked at the HTML behind this app here, you'd see that there's actually an HTML div put in at this point that sets aside some space for a plot to appear in our app. Now, based on the code we've written over here on the left, the app has no idea what sort of plot to put there. All we've done is tell the app we want the name of the plot to be hist, but we haven't explained, do we want it to be a histogram, which I do, a scatter plot, a bar chart. The app doesn't know anything about what sort of plot to put there, so all it could do is reserve some space for it. Now we need to tell the app how to build that plot, and that's something we do with the server function. But before we look at the server function, let's just recap what we've gone over so far. I recommend that you begin each app with the same template, the template we saw there. You may have seen Shiny apps that don't quite look like that, and I'll talk about that by the end of the slideshow today. But for now, start each app with that template. Second, add elements to your app by passing them as arguments to the Fluid Page function. Third, create reactive inputs with an input function. And fourth, create reactive outputs with an output function. And then finally, we're going to use the server function to assemble inputs into outputs. So let's take a look at that. The second thing you have to do when you start building Shiny apps is explain to the server how to assemble your inputs into your outputs. This is what the server function looks like in the template. There's nothing in it at the moment. Inside the server function is where we're going to write our instructions for building the outputs that we see. To use the server function, you need to follow 3 rules. And these are the rules. First, if you're building an output object, you need to save that output object to output $. So this is going to save, for example, an object to the hist element of the output list. An output here is just the second argument of the server function output. Both input and output must appear in your server function as arguments, and they're both going to be list-like objects. So here we're just adding an element to the output list of hist. I'm choosing the name hist because this element is going to be the element that gets placed in the plot named hist. So you use the same name in both files, or in both objects. In the server function, the name is an element of a list, and in the UI object, it's a character string inside of the plot output function. The second rule for using the server function is what you save into output should be something built with a render function. So Shiny provides a third family of functions, and these are render functions. And the render functions work together with the output functions to place an R object as HTML into your Shiny web page. You'll see that just like the output functions, there are different render functions for rendering different types of output. For example, we have render plot, render table, render text. In many cases, there's a direct analog between a render function and an output function, like render plot and plot output. What I would like to do for now in our sample app is to just plot a histogram of 100 random normal values. So rnorm100 is how you make 100 random normal values in R, and hist is how you plot some data. So hist rnorm100 would plot a histogram of 100 random normal values. I'm going to use render plot to do it. Let's look at the syntax of render plot. You'll notice that all the render functions begin with render, and then the second argument is the type of object to actually build. In camel case. In this case, I'm going to build a plot. A histogram is a type of plot. The next argument of the render functions is a code block of R code that builds the object you want to make. So we know this code here will build us a histogram to render as a HTML object in our Shiny graph. I'm putting braces around the code to pass it as a unified code block. What the braces let me do is put as many lines of R code as I want into the same code block to pass to render plot. So for example, I could build my histogram like this. I call render plot. I have the braces. I have one line of code in there. Or I could take my time and develop this plot a little more fully. Now I'm using 2 lines of code. First, I'm writing a title, then I'm adding the title to the histogram. And the braces will group those 2 lines together and pass them as a single chunk to render plot to build the histogram. You could put 100 lines of code between the braces. You could put an entire R script between the braces. And this is how you could start building really sophisticated outputs with multiple lines of code going into their making. Just surround everything with braces and pass it to render plot. So that was the second rule. There's just one rule left to create objects for Shiny, reactive objects no less. And that rule is to use input values when you make your outputs. And you could access input values with a syntax similar to the output syntax. So what I mean by input values are the values of the drop-down menus, sliders, action buttons that you put into your Shiny app. Recall that we made a slider input in our app and we gave it the name num. Well, inside of our server function, the value of that slider will be accessible with the syntax input $num. If I had thrown in a second slider and gave it the name num2, then I could access its value with input $num2, and so on. These values of the input functions are special because they always show the current value of the input. So when that slider is set at 25, the current value of input $num will be 25. But when the user moves the slider to 50, then the value of input num will change to 50. And if the user moved it to 75, the value would change again to 75. So when you look up input $num, it'll always show you the current value of the input as set by your user. If you want your output to depend on these values, just use the values inside of the render function when you create the output. So here, instead of making a histogram of 100 random normal values, I'm going to make a histogram of n random normal values, where n is a number set by the user with the slider. Sometimes it might be 25 values, sometimes it might be 100 values. It's up to the user. If you follow these 3 rules, you save your output to an output object, you use a render function to make the output, and you have the output depend on input values, then reactivity will take care of itself. Shiny will handle that for you. Whenever input $num changes, the output saved as hist will immediately update to reflect the change. This is what it looked like graphically. We have our app on the side here. The first time we launch the app, Shiny runs the code inside of render plot. The code is hist rnorm input $num. You'll notice as part of running that code, it's going to access input $num and it needs to look up that value. And when it does, Shiny's going to build a connection between this plot and that value, input $num. And it'll keep track of the fact that the 2 are related. If a user comes along and changes the slider, for example, they move the slider from 27 to 25, well, then the value of input $num will be different. When this happens, Shiny will look at all the things connected to that value, all the things that rely on the value, which includes render plot, and it will notify them that they're now out of date. When render plot knows it's out of date, it automatically reruns its code to make an up-to-date graph. In the process, it looks up the new value of input $num when that code calls input $num. It gets that value, which is 25, and it uses that value to make a new plot. And then the cycle is ready to begin again. This is going to happen so fast that to your users go appear instantaneous. And now whenever they change the slider, the plot will update as well. And that's called reactivity. So let's pause for a moment and just recap what we learned about the server function. You use the server function to assemble your input values into outputs. And when you do this, you should always follow the same 3 rules. First, save the output that you want to build to the output list. If you do that, the output will be accessible by the UI object when you call plot output or text output or whatnot. Second, build the output objects with the render function. The render function helps assemble them into HTML for their final appearance, and it also keeps track of the reactions and the reactivity. And third, access input values with input $ syntax and use them inside the code that you pass to render plot. If you do all 3 of these things, Shiny will make sure the reactivity works for you. The reactivity, in other words, will take care of itself as long as you follow those 3 rules. All right. Now you know how to build your own Shiny apps. And soon we'll look at sharing your Shiny apps. Before we do, let's go back one more time to RStudio. Stop the live app here. And what I want to say is that the last piece of code that I've included with the slides is O2 Hist app. And this is the actual app that we just talked about in the slides. If you run this code in the command line, hit enter, it will launch the app we've been looking at. Now I can make it skinnier so it looks more like the slides. And you'll see that whenever I change the slider, the histogram adjusts. Sometimes the histogram shows almost 100 different observations in the format that a histogram does. And I can also make it show just, a couple observations, one observation. So there's our reactive Shiny app. Go back to the slides. So when it comes to making Shiny apps, that's as simple as it gets. You could use those things and make your own apps. And depending on the R code you use, your apps can do all sorts of different things. Now, there are definitely beginner level apps, and in the next 2 weeks, we'll look at how to expand them into more advanced, sophisticated apps. But before we do that, I want to cover how to share your apps, because this is one of the most essential parts of a Shiny app. We make Shiny apps to share them with others or with ourselves, and it's no coincidence that Shiny apps are fundamentally a web page. This allows us to share them over the web. To share your app over the web, all you have to do is arrange to replace your own computer, which shares your app locally, with a web server that can share your app over the cloud. In the very beginning, I suggest that you do this. Well, let me refrain from my suggestions and say, no matter how you arrange to put your app on a server, you will need to save it in a standardized way. Every web server that can handle Shiny apps will expect your app to come packaged like this. You should put your app in any file that the app relies upon, like an image or some CSS style sheets, helper scripts, other R sources. Put them all in the same directory. And then your script that began with the template and ends with the call to Shiny app, save that as a standalone R script in your directory that has the name app.r. You need to use this name. The Shiny server will look in the directory for a script called app.r, and when it finds it, it will use that script to build your app. So remember that name and use it. Now, in the beginning, it was not possible to build a single file Shiny app like we've been doing today. In the very beginning of Shiny, every Shiny app was 2 separate files, a file for the UI and a file for the server. And this format still works, and it's still very useful on certain occasions. The relationship between a 2-file Shiny app and a single file Shiny app is very straightforward. In the 2-file structure, you take everything that you would save to the UI object, and you just put it in a standalone script. You don't need to save it to UI. You just put it in its own script, and you name that script UI.r. And then everything that you would save to the server object, you put that in its own script, and you save that script as server.r. And with these 2 scripts, neither of them calls Shiny app. You don't need to call Shiny app in this scenario. If you have a very, very large app, each of your UI and server objects takes hundreds of lines of code, it can be very beneficial to split your app up into 2 separate files like this. If you do it, this will still work. This technology still works with Shiny, and it always will. If you're building your apps in this way, then when you save your apps, instead of saving a file named app.r, save your 2 files as server.r and UI.r. Again, you need to use these names. Shiny servers will first look for app.r. If they don't find a file called app.r, then they'll look for a pair of files with the names server.r and UI.r. Okay, now you should be able to package your Shiny app into a directory to give to a server. You'll notice that packaging your apps in this way has some other benefits as well. If you save your app files as UI.r, server.r, or app.r, then RStudio will recognize that these files contain components of a Shiny app, and it'll add a Run App button to the top of the page that displays the script. You could click that Run App button to launch your app. So instead of typing in the command line, you could just click the button to launch your app. Not only that, next to the Run App button will be a drop-down menu that lets you choose how to display your app. So if we go over to RStudio, stop this app. You notice app.r, the clustering app, is saved as app.r, and Shiny recognizes because of that file name, or RStudio recognizes because of that file name that it is a Shiny app. I could click Run App to launch the app. There it is. Go over here, stop the app. Next to Run App is a drop-down menu. If you select Run External, it's going to do what we've seen. It'll launch the Shiny app in your own web browser. But you could also select to launch the app in a pop-up window like this. Or something that I think is particularly cool is to launch the app in a viewer pane. The viewer pane's over here in RStudio. When you launch an app in the viewer pane, it appears right here inside the RStudio IDE, which is nice and organized and concise, and I kind of like it. All right. Now that you could package your app up to share it, I recommend that as you start out, you just use shinyapps.io. Shinyapps.io is a free service run by RStudio that allows you to share your apps online when you want to. You could think of it as a server that RStudio built and maintains for you. It's free to use. It's easy to use. All you have to do is put your app on our server. It's secure and it's scalable. So when multiple people start visiting your app at the same time, the server will wind up extra R processes to handle each person individually, so no one experiences a sort of slowdown in number crunching since multiple people are using the app. To use shinyapps.io, all you have to do is to get your app from your computer to our server, and doing that is very easy. Just visit the website shinyapps.io. This is what it'll look like. So let's come over here to Google Chrome. If you go to shinyapps.io, the web page looks like this. You can sign up for an account right here. Now, I already have an account, so all I need to do is log in. When you do sign up or log in, you'll see that you could create your own shinyapps.io account, or you could just associate with your Google login or your GitHub login. So I use my Google information to log in. So log in. This is what you'll see once you set up your shinyapps.io account. It's a dashboard for your apps and whatnot. But to use your Shiny Apps account, you need to associate your RStudio IDE with your specific account on shinyapps.io. And the way you do that is you install a package called Shiny Apps. This package isn't on CRAN. You have to get it from GitHub. And if you don't know already, the way to install packages from GitHub is to use the DevTools package with the command install GitHub. And you don't have to memorize all this right now. I'll show you a guide that will step you through this. But what this is going to do is it's going to go to the RStudio GitHub page and install the Shiny Apps package from there. I already have it installed, but you can see how it works. Just hit enter. Once you install Shiny Apps, the first time you run it, a pop-up window will appear in your RStudio session, and it will tell you to do this. It'll say, basically, hey, I want to know which Shiny Apps account you want me to start sending your apps to, so please log into your Shiny Apps account, go to your username, and go to tokens. And in the token is a token pair. One of them is secure. You can see the secure one by clicking show, and then you can copy and paste it. And then you'll go back to RStudio and paste the secure token in here. And this is how RStudio will know which Shiny Apps account to pair your IDE with. Once you have that set up, every time you run an app, you'll have an option in the top corner to publish the app. If you click publish, it'll say, hey, do you want to publish this app at the shinyapps.io gallery or your account? You could say cancel if you click the button by accident, but if you do want to publish it, then you can just click publish. And it takes a few minutes, but it basically looks at everything your app uses, builds it into a standalone package, and sends it up to shinyapps.io. And when it's done, your app will have its own address. So I'll let this run in the background. I already have plenty of apps here, so I'll show you what you see. For each of your apps that you have on shinyapps.io, you get a dashboard for the app. First thing to notice is the app has its own URL. So this is an app that appears, well, here's our K-means clustering app. It just got loaded and now it has its own URL. Let's look at something a little more interesting. This is an app in the Shiny Gallery. Sort of recreates the Hans Rosling sort of Gapminder effect. But here it is. Anyone can visit it by going to gallery.shinyapps.io/Google Charts. They don't need to use RStudio. They don't even need to have RStudio on their computer. All they need is the web browser and they can see and use the app. Since I'm the owner of the app over here, I could download the files of the app to my computer. For example, if I'm logging in from a different computer, or if somehow I misplaced the original files. I could look at metrics for the app, see how many people are visiting it, how much memory the app's using as people visit it, and so on. I could tweak the settings of the app, things that make the app run faster, things such as when will the app time out, when people start going idle on it. I could decide if the app's going to be public or private. If it's private, then I could add authorized users down here. These people will have to sign in with their Shiny Apps account or their Gmail account or their GitHub account to see the app. I don't want to make this one private because it's public facing, so I'm going to keep it public. I could look at the logs of the app. These are the things that the server gets. Excuse me. These are the things that the server sees as your user uses the app. So as your users navigate through the app, if the R commands of the app fires off, print anything to the server, to the R console, you'll see them here. This is where error messages or warnings would appear. So this will help you understand what your app's doing when it misbehaves. And you can download the log files to your own computer by clicking the button. You could restart your app if you think things have gone wrong. It just needs to be restarted. And you could rebuild your app from source by clicking the rebuild button. And then finally, if you have an app on shinyapps.io that you no longer want to be online, you can archive the app. shinyapps.io will take the app down from its URL. People won't be able to visit it anymore, and the app will just be archived in your account. It's very simple to relaunch the app since it's stored in the archive, but you don't have to do that. If you would like to use shinyapps.io and you'd like something to help you step through those simple but 2 initial steps, visit this website. It's a guide to getting started with shinyapps.io. It'll step you through everything that I just mentioned and help you start using Shiny Apps to host your own apps. In the beginning, Shiny Apps is free. If you're a small account and you don't consume too many resources, it will always be free. But if you do something like teach a large course that you want to use your Shiny Apps on, so you have a lot of people visiting your apps, or you're a consultancy or some sort of business that uses this on a professional level, then you might want to consume more resources. And we have some paid plans that you can use for that sort of activity. Now, shinyapps.io is production ready. It's ready to use in a commercial setting. And these more advanced tiers here help you take advantage of all those resources. But like I said, in the beginning, since we're all just starting out, it is completely free. And depending on what you do with it, it can remain free for the rest of your life. Now, you may not like the idea of hosting your apps on someone else's server, even though that server is our studio server. We promise to be nice and not misbehave, but you have the freedom to create your own server, and we've built a product that can help you do that. It's called Shiny Server, and what it does is it's a backend program that built a Linux-based web server that's specifically designed to host Shiny apps. Shiny Server is completely free, and it's also open source. So you could download this and use it to set up your own server to host Shiny apps on the internet or maybe on an intranet inside your company. If you want to learn more about Shiny Server, you could do so at the web link there. If you plan to use the server in a commercial setting, we spend a lot of time enhancing Shiny Server with features that would be appealing and create value in the commercial environment. We call this product Shiny Server Pro. It's no longer free, but you can try it out with the 45-day free evaluation trial. What it has that the regular Shiny Server does not have is more secure access features such as LDAP, authentication, Google authorization, and so on. More ways to fine-tune performance, make the apps scale more smoothly. We've invested a lot of time creating ways to monitor and manage resource use in the server, so you get an administrative dashboard, and you can look at each app individually and users and see who's accessing and using what, and to set some constraints there. And then finally, since this is a paid product, we do provide direct priority email support for Shiny Server Pro customers because we reinvest what you pay us to hire a support staff. If this interests you, you can learn about Shiny Server Pro at the same place you learn about Shiny Server at that web link up above. So let's recap the ways to share your apps. The first thing you need to do to share your app is to save it in its own directory with one of the predefined names for your R script. Next, you could host your apps at shinyapps.io by signing up for a free shinyapps.io account or installing the Shiny Apps and then installing the Shiny Apps package. And then finally, you could build your own server to host your own apps at with Shiny Server or Shiny Server Pro. So we're near the end of the webinar, and let's look back at what we've learned. You've learned how to build a complete app with inputs and outputs. You've learned how to arrange things so reactions happen automatically by writing the server function for your app. And you've learned several options for sharing your apps. So now you're ready to go. You have a complete tool belt to use with Shiny. You'll want to put some more tools in that belt as you go along, but you can make basic functioning, useful apps today. If you want to learn more, and I hope that you do, then come back for the next 2 webinars. We'll take a deep look at how Shiny creates reactivity behind the scenes and how you can customize and tweak that process. You'll learn things such as how to delay reactions till your users click a submit button, or how to use buttons and widgets to trigger code on the server side that does more things than just create a plot or a table to put back in your app. The week after that, we'll look at how to customize the appearance of your apps to make them as pretty and as attractive as you like. Since our apps are basically web pages, as you can imagine, we could do a lot with HTML, CSS, and JavaScript. And surprisingly, a lot of that functionality is already embedded into Shiny, which means you can use R to customize your apps. You don't need to know HTML or CSS. In the meantime, if you want to learn more about Shiny, I recommend that you go to the Shiny Development Center. It's at shiny.rstudio.com. There you can find a gallery of Shiny apps with the code that built them. These are all teaching examples that you can learn from and recreate. There's a tutorial that you could take. It's self-paced. And then finally, there's a section of articles that cover advanced Shiny topics in depth. There's about 50 articles there, so there's a lot to learn. All right. So that's the end of today's webinar. And now I think we could take some questions. All right. Before we get started, in addition to the regular place where Bill and Roger put all of our RStudio webinars, I've also put the slides and the code for today at this bit.ly link. And just like last time, the bit.ly link will persist at the top of the slide deck. So you'll see it throughout the webinar today. You don't need to write it down right away. But if you want to follow along with the code and the slides, you can visit there and download the materials. It's about 5 megabytes. And then just like last time as well, I'm going to be looking at some really simple examples of Shiny to make things easier for learning. There will be no bells and whistles and no distractions in these examples. And I don't want anyone to get the impression that Shiny only makes really simple apps. If you would like to see Shiny apps used to their full extent, or the way people, at least in the business world, use them, please visit the Shiny Showcase, where I've collected many examples that show off more of the capabilities of Shiny beyond what we'll learn today. So this is the second of a 3-part webinar series. The first part was an introduction to how to build Shiny apps, and it's now available at this web address. And so if you missed that webinar, you could check it out and watch it for free there. Today we're going to look at how to customize reactions in your Shiny apps. And then a week from today, we'll look at how to customize the appearance of your apps. So if you notice that our apps look kind of plain and we haven't done much with the layout or the visual appearance of the apps, don't worry, that will be the topic of the last webinar. So let's review where we left off last week. During that webinar, we learned the basic architecture of a Shiny app. Every Shiny app is a web page that contains R components. And attached to every Shiny app is some computer, normally a web server, that is running with an open session of R. And when a user changes an input on the web page, for example, selecting something from a drop-down menu, then that server running R immediately responds by generating some new R output to place in the web page. For example, they might generate an up-to-date graph or an up-to-date table. And so this idea of a web page and a computer running R is fundamental to the idea of a Shiny app. We looked at a template for building Shiny apps in the last webinar that involved 4 lines of code. And the template revolves around building a UI object, which lays out the web page for the app. This object will eventually be written in HTML, but you create it with R functions using R code, so you don't need to know HTML to make a UI. And then you write a function for the server to use to create the R components for the app. This is where we'll spend our time today. We'll focus on writing the server function. And then finally, the template knits together the UI and the server components of the app to create a full-fledged Shiny app. We use that template to look at the basic components of an app. We learned how to add inputs to your app with input functions provided by Shiny. For example, this function adds a slider to an app. We looked at how to add space for output objects. These are the display objects you build with R but show to the user in your web page, with the output functions, which also go into the fluid page function that's saved into the UI object. We learned that even though you've provided space for an output object, you still need to build the output in the server function using the computer that's running R, and that you do this in a three-step process. Every output you want to add to the app, you have to save in the server function as output $, a name, and that'd be the same name you looked up the output with in the UI file. Second, you build the output to display with a render function. For example, render plot would render a plot, but there are other render functions that render other types of things. And third, in the code you use to actually build the output, if you use an input value, which you can access as input $, in the name, Shiny will take care of reactivity for you. So if you make an output that uses an input value, then whenever that input value changes, so long as you follow these basic rules, the output object will change as well. It will be connected to the input object and it'll stay up to date. During the course of that webinar, we made this app, and I'll use it as an example app for some of the examples today. It's just a simple app with a slider and a histogram that changes when you change the slider. And then we ended that day by looking at how you could share your apps. Shiny Web Apps are web documents, so they're made to be easy to share over the internet should you choose, or some other HTML-based intranet. You could share all of your apps for free on a server hosted by RStudio called shinyapps.io. And I explained that to get started with shinyapps.io, you could just visit that website, shinyapps.io. And I also explained how you could build your own server using either the open source Shiny Server product or the professional version of Shiny Server. And both of these just build a Linux server that you are in control of and you own to host your Shiny apps on the internet. If you don't believe we went over all these things, or you didn't attend the last webinar, you can find it here at this link and check up on all these facts. And I encourage you to do so. Going on for the rest of the day, I'll assume that you have a basic acquaintance of the material we covered in the last webinar. So let's start with reactivity. I think the easiest way to think about reactivity or get an intuition for reactivity with Shiny apps is to think about Microsoft Excel, because Excel is probably the most common place where we find reactivity in our day-to-day lives. If you open an Excel table, a spreadsheet, you could type some value into a cell, and then you could go to a new cell and type in a formula that uses the old cell. So this is a formula that takes the fourth row of the F column where I typed 50 and adds 1 to it. Once I hit enter, it computes that formula. And now whenever I change the cell in the F column, the cell in the J column will react. It will automatically update, so it's always equal to the F cell plus 1. This is reactivity, and this is also what Shiny does. The effect of this is that it seems like changes in the F cell are propagated over to the J cell. In Shiny, we do something similar, but instead of working with cells, we have input objects and we have output objects. And changes in our input objects get propagated to the output objects, as if there were 2 cells in a spreadsheet. Of course, there are no spreadsheets involved. Instead, our input objects are things like sliders and action buttons and drop-down menus, web elements that your user can manipulate. And our output objects are things to display like tables, graphs, visualizations, that sort of thing. Now, in Shiny, reactivity is much more sophisticated than just inputs and outputs. We could also do things like this. We could use a change in an input object to trigger some arbitrary code to run on the server side, or we could extend our chains of reactions, so we could have changes in inputs create secondary objects that are themselves reactive, and changes in those objects can trigger changes in our outputs. We could control our reactions. For example, we could insert something like an update button into our app, so a change in an input will eventually change an output, but not until the user asks it to by clicking the update button. And these sorts of things are going to provide the material that we go over today. We'll go look at how to start with inputs and create all these different patterns of reaction within your Shiny app. We'll go begin with reactive values, because that's where reactivity starts with Shiny. So we know now that you can create an input object with an input function, and you could give that input function a name with the input ID argument. Once you do that, the value of the input function will be available to use in your code in the server function. So for example, this input function here creates a slider, and every time the user changes the slider, the value of that slider input, named input $num, will change as well. So the value will always show the up-to-date value of the slider object. This is what a reactive value is. It's a value that changes, reacts to some sort of input. And it's different than other R values because it can change at a moment's notice. Most values in R only change when there's a piece of code that actually tells them to change. And normally you're the person who writes that piece of code. These are a little different. Reactive values in Shiny don't work on their own. They actually work together in relationship with a function, a reactive function. Reactive function is a term I'm just going to use today, and all it means is a function that expects to take reactive values and knows what to do with them. These two ideas, reactive values and reactive functions, work together to create the reactions we'll see in Shiny. And so if you try to do something with only one of these components, for example, if you try to use a reactive value like input $num, but didn't pair it with a reactive function like render plot, which we were using last time, you'd get an error. In fact, this is a pretty common thing to do in Shiny. Notice in the app that we made last time, the code's over here on the left, we're using a reactive value to create this histogram. And we're using a reactive function, render plot. It's a function that expects to take reactive values and knows what to do with them. And together these things create the app that we see. If we decide not to use render plot, or we forget to use render plot, and just call the reactive value, you'll get this error message. And as a beginning Shiny developer, this will be a very familiar error message, so we should take a look at it. It says, the operation is not allowed. You're doing something and not doing something in an active reactive context. This is technical speech, but all it means for you is that you try to use the reactive value without also using a reactive function to work with it. And if you see this error message, it means you need to think of what reactive function you want to use to do what you're trying to do. Now, I've said that render plot is a reactive function, but we'll see today that there's more functions you could use besides just render plot. So this idea of reactive values working together with reactive functions breaks reactivity in R into a two-step process. Now here's a visualization of the app that we made last time. You'll see that this app has a reactive value created by the slider. That value is named input $num, just because of the way we wrote the code. And then this app has a reactive function, render plot, that is using input $num to create an object that's being saved to output $hist. I'm going to call this object created by the reactive function an observer. And together, the observer and the reactive value create the reactivity in the app. When you change the slider, here we'll change it from 27 to 25, it changes the reactive value input $num, and then the reactive value does its job. The job of reactive values and reactivity is to notify things downstream that they've changed. So step one, the reactive value notifies the objects that depend on it that it has changed. And now its job is mostly over. It's time for the reactive function to do its job, or more precisely, for the object created by the reactive function to do its job. And what its job is to just respond in some way. When you have a render function, it creates an object whose job is to rerun the code that you pass to the render function to update itself. So here, once notified, output hist will rerun the code. The code calls input num, so look up the value of input num, and once it has it, it can create the new graph and put it into the plot. So those are the two steps of reactivity. Reactive values notify the things that depend on them that they've changed, and then the things that depend on them respond in some way. The way to customize their response is to use the correct reactive function to do what you want to happen. Which means our job today will be to learn what are the different reactive functions we can use and what are the things that they do. So let's just recap reactive values before we look at all the functions we have at our fingertips. Reactive values act as a sort of data stream that flows through your apps. They're the changes that cause reactions downstream. The input list in your app is a list of reactive values, and these values are designed to always show the current state of the input objects in the Shiny app. You can only call a reactive value from a reactive function, which is a function that's designed to work with the reactive value. And then finally, you could think of reactivity in R as happening in two steps. Reactive values notify the things downstream that they've changed. This is a process called invalidating. So a reactive value notifies an object that has become invalid, and then the object, which has been created by a reactive function, responds in the way that that function programmed it to respond. To completely control reactions in Shiny, there's only about 7 functions you need to learn. I'm going to call these the reactive toolkit. So let's take a look at these functions one at a time. The first one will be familiar. But as we go through the functions, it can help to think of 2 things related to the functions. Almost all of these functions are going to take a chunk of code, and they're going to use that code to build and rebuild some sort of object. And then second, the object created by the reactive function will respond to changes in a set of reactive values. It will be notified by certain values or invalidated by certain values using that vocabulary. If you want to understand these functions at a deep level, then when we go through them, I suggest you ask yourself 2 questions. First, for each function, ask yourself, what code will the function actually use to build the object or rebuild the object? And second, ask yourself, what reactive values will the object created by the function respond to? So it'll normally be obvious what code the function is going to use, but it'll be a little more subtle to understand which reactive values the object will respond to. But of course, that's a very important part of the process, and I'll try to make it clear. The first set of functions in the reactive toolkit are the render functions, which you've already seen in the last webinar. So Shiny comes with a family of functions that each create a certain type of output that you can display in your final Shiny app. The most common of these functions are probably render plot, render table, render text, and they build something that can actually be displayed. To use one of these reactive functions, you just need to give it one argument, and that's a chunk of code or a block of code that the function uses to build the display object and to rebuild the display object whenever it changes. This block of code should begin with the curly brace and end with the curly brace. Between the curly braces, you can put whatever you want. You can even put multiple lines of code. You could put 100 lines of code if you want. The curly braces will unify that code together so it can be passed on as a single block of code to the object that RenderPlot makes. This object will respond every time a reactive value in the code block changes. So you could have 1 reactive value in that code block, you could have 10 reactive values, you could have 0 reactive values. But whenever a single value changes, the object created by RenderPlot will be invalidated, which means it will, in this case, rerun that code to build a new version of itself that is up to date. And this is an important point. When you pass a block of code to RenderPlot, that block will always be run as a single unit. When it's time for the object, for example, the graph that RenderPlot makes, to be re-updated, that entire block will be run. RenderPlot can't do anything to determine, which parts of the block are out of date and just run those parts. It just always runs the whole block of code each time. So let's take a look at how that works out. In the downloads for today, there's several R scripts. This is the first one. And it just creates a simple app that has 2 input objects, a slider and a text field where you can write a title. And then it uses those to make a histogram. One thing you'll notice is that histogram uses both of the input objects. So it uses 2 input objects to do its job. You can visualize the app like this. Here's our 2 input reactive values. And here's the observer object created by RenderPlot and saved to output hist. If you were to type a new title into the title field, for example, I'm going to try to change the title to very interesting data, then the reactive value input $title will change, and it will notify everything downstream that depends on it that is changed. This notification invalidates output $hist, and since output $hist was made with a render function, it's going to respond in a certain way. It's going to rerun the block of code in the render function to update itself. When it runs that code, it's going to call input $num, even though input $num hasn't changed. It's just running hist rnorm input $num. It gets that value, and then it gets the main equals input $title, and it gets that value. And once it has both those values, it can make the new plot, which will then appear in our app. So that's pretty straightforward, and that's very close to what we looked at last week. And that's how the render functions work. They make objects to display. Whenever you want to make an object to display in your app, you're going to use a render function. You always save the results of the render function to output $, because that's the only way to get the results into your app. And then the render function makes an object, an observer object, that has a block of code associated with it. That's the code chunk you pass to render plot. And whenever that object becomes invalidated, it will rerun that entire block of code to update itself. So that's pretty straightforward. Let's look at how we can make things slightly more sophisticated. Here's a similar app. This app has one input, a slider, but it has two output objects, a histogram and then a block of text, which includes summary statistics at the bottom. And you'll see over here on the left, I'm making that block of text with the new render function, render print, which renders the output of what gets printed into R. Each of these output objects use the same input object, input $num, which means our app looks something like this. We have one reactive value, two things depend on it downstream. When that reactive value changes, for example, when we move the slider, it notifies both of those objects that they're invalidated, and then these objects rerun the code blocks to update themselves. So first, the histogram will rerun its code block. It's going to generate input $num random normal values, and it's going to plot them as a histogram. And then the second observer object, output $stats, will rerun its code. It's going to generate input $num random normal values and print out the summary of those, and that updates that part of the graph. Now, one thing about this arrangement is we're calling rnorm input $num twice, once for each object, which means each object is generating its own data set to describe. The histogram is describing one data set, and then the summary statistics at the bottom are describing a second data set. Now, that's not generally the sort of behavior we'd want in this sort of app. And what we'd like to think about doing is make sure that both output objects describe the same data set, which is something we could do. Our strategy for doing this would be to, instead of calling rnorm input $num twice in this app, call it once and save the data set it creates, and then use that data set downstream where we need it. Now, I put a question mark here by the assignment operator because it's not clear yet how we should save the data. First of all, rnorm input $num does contain a reactive value, so we need to use a reactive function to work alongside that value. And second of all, we want this data set to do something specific. It's going to get notified by input $num when it becomes out of date. We want it to pass on that message to things that depend on it, that they too are out of date. So these jobs are what you can do with the function reactive that occurs in Shiny. Reactive builds a reactive object, which is called a reactive expression in the Shiny vocabulary, that takes input objects, assembles them together into some sort of output. Could be a data frame, could be a single value, could be a plot, and makes that output, that result, available to use later on in other code. To use reactive, pass it a code block. Reactive will use this code to build and later on rebuild the object you're making. And then, just like with render, the object will respond to any reactive value in the code block that changes. Reactive expressions sort of emulate R objects. You create them and then you use them again later. But they're actually different in a couple of ways. In the first way, the most important way for avoiding errors, is that reactive expressions are technically functions. And if you want to use it later on in your code, if you want to use the data that we store in data, you'll have to call data as if it were a function. That means you'll have to put an open and close parentheses behind the name data. There's no arguments involved, just open and close parentheses. If you forget the parentheses, then R will do the same thing it does whenever you type in a function name with no parentheses. It'll show you the code inside that function. Now, normally that's not what you're looking for inside your Shiny app. You almost always want to put these parentheses. So if you're getting weird error messages, check and see that your reactive expressions have parentheses behind their names. So if we wanted to use a reactive expression to modularize that app we were looking at, this is how we could go about it. We could take our two instances of rnorm input $num and create a reactive expression that builds the same thing. It calls rnorm input $num. I'm going to save the result of this reactive expression to data, and then down here, for each of the instances of rnorm input $num, I'll replace it with data. So we're building this data set once, and we're accessing it twice. But now, both hist and stats will be accessing the same data set. Let's look at how this works when we start playing with our app. If we were to change the slider now, input $num would notify the reactive expression that it's invalid. And then the reactive expression, what they do is they simply notify the things downstream that they too are invalid. The reactive expression didn't recompute any results or anything, it just passed on the notification. Now we get to the output objects created with the render functions. The job of render functions is to rerun their code when they become out of date. So now output hist is go rerun its code. It's go call hist data, which means go call data. When it does, the reactive expression knows it has to return a value. The reactive expression is out of date, it doesn't know the right value to return, so it now runs its code. And when it runs that code, it looks up input $num, gets its value. The reactive expression computes itself, saves its result, passes that result to hist, which can now make the new plot. And now it's output stats time to return to rerun its code. And here's the second thing that reactive expressions do that's different than regular R objects. Reactive expressions know whether they're valid or invalid. At the moment, this reactive expression is valid because it just looked up the new value of input $num, and nothing has changed since then. Reactive expressions also save their result in your computer's memory. So the reactive expression has two options now for returning a result to stats when stats calls it, which it will. Stats runs summary data, calls data. The reactive expression either recompute its code to arrive at the value, or it could take the value that had stored in memory and just give it to stats, since it knows that value is up to date. Reactive expressions will always just return the value they have stored in memory, their cached value, to avoid computation when they're up to date. So why does this happen? You can imagine a reactive expression that takes 50 lines of code to compute its result, and if it's up to date, there's no sense in wasting time recomputing 50 lines of code. It already has the result stored in memory. It doesn't need to arrive at the result twice, so it just passes on that result. If the reactive expression knows it's invalid, then it runs the code. So you could think of the second feature of reactive expression as reactive expressions cache their values. And the expression will always return its most recent value, which is cached in memory, unless the expression has become invalidated, at which point it reruns its code and saves the new value. All right, so let's recap reactive expressions. They make an object to use. These objects don't appear in your app. Your user doesn't see them, but you could use them in code that does make objects to display. You could use reactive expressions to modularize your apps because they're also reactive, so they fit in as a link in the reactive chain. You call a reactive expression like a function with parentheses behind it. And then reactive expressions cache their values, which can save you computation. Well, it'll save your app computation. In practice, you don't even have to worry about them caching their values. That's just a feature Shiny takes care of for you. So we've learned how to make a chain with render, and we learned how to extend a reactive chain with reactive. Now let's look at something a little more simple, isolate. Here's our app we looked at 2 apps ago. It's the one that creates 2 inputs, or uses 2 inputs to create an output. And if we go over to RStudio, we can actually take a look at this app in practice. If you download the files for today, this is what the folder you get looks like. It has the slides for the day and then the code. And inside the code are 8 different apps to look at. And this one's just the first app. So if I highlight all this code and then run it at the command line, and Command Enter, keyboard shortcut to do that, I get the app over here. You'll see that when I change the slider, the histogram updates. And also when I change the name, the histogram updates. Now it could be that I have a good name in mind, but it could be that I'm a slow typer, and so the app is starting to react faster than I am actually reacting. And at the moment, I don't like that. So I'm going to try to circumvent that behavior. What I want to do is find a way to prevent the app from responding to the title field. So the app will still respond when I change the slider, but in the meantime, I'll have the freedom to type in any title I want, and the app will not respond to that. You could do that sort of thing with isolate. So isolate is analogous to reactive, in that reactive creates some output that is still reactive. Isolate creates output that is not reactive. You give it reactive values to assemble into some output, some result, and then it gives you back the result. But the result itself is just a normal R value. Nothing will react to it. It's not a reactive value. The arguments for isolate are similar to the functions we looked at already. It just takes a block of code that it uses to build its result, but then the result will not respond to any reactive value in the code. The result will be inert. So if we wanted to use isolate in this app, and we only want input title to be non-reactive, then what we would do is we'd surround input title where it appears in the app with isolate. So isolate's go to fetch the value of input title, but it's go give back the value in a non-reactive state. In practice, this means that once we put isolate around input title, the observer object won't have a dependency on input title. It'll use input title, but it won't react to it. So now we can change the title, that'll change reactive value, but there's nothing downstream of the reactive value to notify. So things will just stay as they are. If you change the slider, it's not isolated, so the output object will still depend on it. It notifies that object. And then the output object does its job. It reruns all the code there. First thing it looks up in the code is input $num, but then after it has that, it moves on and it looks up isolate input $title. It's going to look up that value just like it'd look up any value, reactive or not. It's going to use it to create a new plot, so the new title will show up in my plot when it's time to make a new plot, but the plot simply will not react when the title changes. So isolate is pretty straightforward. It makes non-reactive objects out of reactive objects. And you could use isolate to treat reactive values as if they're normal R values to sever the chain of reactivity. All right, let's look at the bigger picture and see where we are right now. We're learning of many different ways to create reactivity. It's a bit technical today, I apologize for that. But we've learned several ways already. We've learned to create the basic chain of reactivity from an input to an output object with the render functions. We've learned to extend that chain of reactivity with the reactive expression. And we also learned how to break the chain with an isolate expression. Now we're going to look at how to trigger code on the server side based on changes in the input objects. So this is code that your user probably will never see, but the server will handle. It could be things like writing a new file to save for later, downloading a file for your user to use. We'll talk about some of the ideas. To do this, I'm going to use a new type of input object called an action button. It's in the same family of functions as slider input is, and it doesn't work very differently. It takes an input ID, it maintains a value that we could access in the server side, and it takes a label. In this case, this label would be click me. And what action button does is it inserts a button input object into your app. So we could add it to the basic template, and we'll get an app that looks like this. It has a simple button in it. I could click that button, but at least when the app looks like this, nothing's going to happen because I haven't written anything in the server side of the app. The way I'm going to trigger code based on clicks of that button is with the function called observe event. Observe event is slightly different than the functions we've looked at before because it uses a different syntax. The first argument of observe event is either one reactive value or a vector of reactive values. And these are the values that observe event is going to follow, to track, to get notified by. So observe event will react whenever one of these values changes. It's going to create an object, an observer object, that exists in your memory. You can think of this object abstractly because it doesn't create a display output. No one's going to actually see this object, but it's going to be there and it's going to react to changes in these reactive values and only to changes in those reactive values. That's important because the second argument of observe event is a block of code to run whenever one of those first reactive values changes. This block of code can contain its own reactive values. It can use them, but changes in those reactive values will not trigger the observe event to invalidate unless those reactive values also happen to be in the first argument. So you could think of this block of code as being wrapped in that isolate function we just learned about, which means you could use these reactive values without pairing them up with a second reactive function. R will treat them just like normal R values. And second, just because the values appear here in this code chunk, they won't trigger the observer to update when they change. All right. So here's how I would use that in my app from before. I'm creating an observer with observe event. Notice I don't need to save it to anything. It'll just appear in the memory for this app. and it'll start working. The observer is going to update whenever I click the button because the first argument here is input $clicks, the name of that button. And then when it updates, it's going to run that block of code I gave it. I can give it any code that R can run. So, really I could have it trigger anything I want. What it triggers will be run on the server side, so it doesn't automatically appear back in the app. You need a render function for that. But let's take this app and see what happens in RStudio. So this script is called Action Button. It's the 5th script. Take a look at here. It's just what was on that slide. And if I run it, it's going to create an app that looks like the app in the slide. It's just a click me button. But you'll notice when I click this button, something's going to appear in my R console down in the bottom corner of the screen. I clicked it once, and the number 1 appeared. Clicked it twice, the number 2 appeared. And every time I click it, something else appears in my R console. Now remember, when you run Shiny apps locally, your R session here is the server for the app. So what I'm doing over here is causing something to happen on the server back here. What's happening is it's just printing the value of input clicks. So here we can see how action buttons work. They maintain a value that begins at 0, and every time you click the button, the value increases by 1. This lets action buttons do their job. The value of an action button isn't meant to be meaningful, it's just meant to create a change that things can respond to. So just out of simplicity, we just have it add 1 each time. That's the change. If you're using action buttons in your apps and you find that your app depends on the specific value of the action button, then there's a chance that you're using the action button inefficiently. In fact, there's a really good chance because your app should never depend on the actual value of the action button. If you want to learn more about action buttons, we've written a whole article on it that you can find here, shiny.rstudio.com. And the article will give you some good advice and best practices for working with action buttons. Along with observe event, which triggers code, there's a second function called observe. It does the same thing. It's a parallel to observe event, but the syntax is more similar to render, reactive, and the isolate functions. With observe, you just give observe a single block of code to run. And then observe will rerun that block of code anytime one of the reactive values in the block of code changes. So the syntax really is similar to render, reactive, and isolate. If you want to use that syntax, then use observe. I found in practice and in teaching people that the precision of the observe event is both easier to think about and tends to be more useful in the long run. But observe is an option. All right. So let's recap what we learned about triggering code. Observe event triggers code that gets run by the server. This is a good way to do things in the background like connect to databases, download data, save data, write to files, do anything else that the server might be interested in. Observe event lets you specify precisely which reactive value should invalidate the observer. Usually you'll put something like a button into your app, and observe event will track that button. So when the button's clicked, it will invalidate the observer. You could use the more implicit general syntax with the function observe, which does the same thing as observe event. It triggers code to run when it is invalidated, but it tracks every reactive value in the code that you give observe. All right. So usually once people get the handle of these things, creating reactive chains, expanding them with reactive expressions, the next thing they want to do is delay reactions. In fact, you might have thought that when we used isolate to prevent the title of our histogram from updating the plot, that was a bit excessive. We could have just delayed the reaction until we were done typing the title. Well, you could do things like that in Shiny. I'll show you how. I'm going to use our basic app from the last webinar as an example. It's a histogram and a slider. And what I want to do is add an action button to this app, which is easy enough to do. And this button says update. And my thought is I would like the slider to not change the graph. I would like the update button to change the graph. So in other words, I'd like to be able to move the slider as much as I like, but not have the graph respond until I click the update button. The way to do this in Shiny is with the function event reactive. Event reactive makes a reactive expression just like reactive does, but it has a different syntax. The syntax of event reactive is much more similar to observe event. The first argument you give it is either a single reactive value or a vector of reactive values to respond to. and only these values will invalidate this reactive expression. The second argument is code that it will use to build the object and to rebuild the reactive expression object when it's invalidated. But just like with observe event, it'll treat this code as if it's been isolated, so it will not respond to changes in the reactive values in that code unless those values explicitly appear in the first argument. We can use this idea to make our simple app to delay the reaction in the simple app. In the output, I'm making a histogram that depends on this data set that I'm creating with input num. There's no real reason to use a reactive expression here because the app is so straightforward, but I can use a reactive expression. There's no reason not to. And what I'll do is I'll create a reactive expression with event reactive. This reactive expression will invalidate when the go button is clicked. That's the button that says update up there. And when it's invalidated, what I want it to do is recompute the data set using the code I'm using below, rnorm input $num. And then down below, I will use the reactive expression, instead of rnorm input $num. So now the histogram depends on a reactive expression that only invalidates when someone clicks the button. If we look at how this app works, if we visualize it, see there's now two input objects, the slider and the go button. And there's the reactive expression and the single output. When you change the slider, that reactive value changes, but there's nothing downstream for it to notify. When you click the update button, the input go value changes, and it is associated now with this event reactive, so it notifies event reactive. Event reactive knows it's invalid. It does what every reactive expression does. It tells everything downstream that they too are invalid. Here the notification gets to an observer created with a render function, so that observer is going to rerun its chunk of code to update itself. When it updates itself, it calls the reactive expression. The reactive expression has been called and it knows it's invalid, so it's going to rerun its code. When it does that, it's going to call input $num. So it will retrieve and use the most up-to-date value of input $num. It just won't take a dependency on it. And once it computes itself, then the output can use that new data set to recompute itself, and we get our new graph. All right, so this is how event reactive works. You use event reactive to delay reactions. It creates a reactive expression, so you have to call the results as a function, just like with other reactive expressions. But you can specify precisely which reactive value should invalidate this expression. And usually you pair event reactive with an action button, but you could pair it with any sort of reactive value. All right. Go look at one last thing about reactivity in Shiny before we call it a day, and that's managing state. And this is a little bit about what I mean by that. We know that we have a list of reactive values in our app that we can work with. These are the input values. And those values will change based on user input. However, we can't change those values ourselves programmatically. You can imagine trying to set the slider to 25, and for your user, that would be a spooky experience. The slider moves back to 25. It might seem like your app was haunted or something. So as a general rule, Shiny doesn't give you the power to overwrite the input values in your app. But every once in a while, that sort of thing would be a useful thing to do. So what Shiny does give you is the power to create your own list of reactive values, which you can then overwrite as you see fit. Reactive values is a function that makes a list of reactive values. It's similar to the list function in that it doesn't take any arguments. I mean, it doesn't require any, but you could give it arguments to populate the list when you create it. So for example, this expression up here, it's going to create a reactive values list that begins with one element, named data, and that element will have inside of it 100 random normal values. I could add extra elements later after I create the list using the list syntax. I could write RV $data2 and save something in the data2 and so on. This is how I would use this in practice. Here's an app. It's the last script in your code folder, and it'll be easier to look at in RStudio. So we'll go here, opening 8reactivevalues.r. Let's run the code and then look at what it does. I'll stop the previous app, run this app. And what we see here is a simple app. It just displays a data set and a histogram. It begins with a normal data set, but if I click the uniform button, it displays some uniform data. If I click the normal button, it displays normal data. I could click the normal button again, it'll generate new normal data, and I can go back and forth. If we visualize this app in our slides, it looks like this. We have a reactive variables list that I created with one element named data, and downstream from that list is a histogram created with render plot. It takes a dependency on this reactive value $data object. When I click either of these buttons, it just overwrites the value of RV $data. If I click the norm button, that's the one that says normal, it overwrites that value with 100 random normal variables. When that happens, since RV $data is a reactive values object, it notifies the things that depend on it that it's changed. So now output hist knows that it's been invalidated, it reruns its code, looks up that value, creates the new plot. Something similar happens when I click input $unif. It overwrites RV $data with this time 100 uniform random values. That's a change, so output's notified, retrieves the new data, makes the new plot. And this is what I mean by managing state. We've created some persistent state here in RV $data, and now we're just programmatically manipulating that state through these action buttons. If we look at the code that does this, see that I created the reactive values object in the server function. That's where you should create them. I'm using observe event to run code that overwrites RV $data each time someone clicks one of those buttons. Now, one thing you'll notice about reactive values lists is that they share a syntax similar to environments in R, which basically means they're easier to look up from inside things like observe event. This code right here will find RV on the search path. I don't need to use a double arrow or anything like that. Shiny will take care of everything for me. Once I have this set up, my app will work as we described. All right, so reactive values, they create a list of reactive values for you to use. Then you can manipulate these programmatically, usually with observe event and some sort of action button. All right, so what do you now know how to do? Quite a bit. You can render reactive output with render. You can modularize your reactive chains with reactive. You could isolate values so they stop the reactive chain with isolate. You could trigger arbitrary code with observe event or observe. You could delay reactions with event reactive. And you can even create your own reactive values to use at the start of your reactive chains with reactive values. So this is probably the most technical of the 3 webinars, and I thank you for paying attention this long. You can see that you've learned quite a bit about customizing your Shiny apps along the way. Before we stop, I want to leave you with 2 parting tips. And the first is to keep in mind what the end result of your Shiny application is going to be. If you are going to host this application online, for example, a Shiny Server Pro, it's going to end up having an architecture similar to this. You write one single application, it gets hosted on a server. In the world of virtual computing in the cloud, that means that there will likely be multiple instances of this application existing as more and more people visit your app. Amazon will fire up instances to handle those people. You can ignore all that. But as people come to visit your app, each server instance will open up new R sessions to handle those people. A single R session can handle multiple people using your app, but you can imagine somewhere along the way when 100 people are trying to use the same R session, your app might start to slow down. So the server is designed to open up a second R session when needed, or a third R session to handle additional people as they show up. And then each person, when they get to the app, they have their own fresh copy of the app, and they experience their app and no one else's app. It's all very secure. But this hierarchy of R sessions and users affects how you should write the code in your Shiny app. Depending on where you place your code, it will be repeated multiple times. If you write code and you place it outside of the server function, it will be run just once each time a new R session is created. So think of your computer. When you write a Shiny app on your computer is the server. Your R session is the session that's serving that app. You can define the UI object just one time, the whole time you have your computer on. You could call library Shiny just once the whole time you have your computer on. Those things will persist throughout the life of that R session until you close R. In fact, we could run everything but the last line of this Shiny template here just one time, and they'll stay in our memory. And then every time we call Shiny app UI equals UI server equals server, We'll use those things we define just once. We might use them multiple times if we call that function multiple times. If you only need to run your code once to set up the R session, for example, to load a help file or load a library, place that code outside of the server function. Code that appears inside the server function will be run once per user who logs into your R session. Now that's a little harder to imagine when you're working locally, but if every time you fire up an app on your R session, that's like a user appearing and using your app. When you close the app and fire it up a second time, that's like a second user appearing. And you can see already that there will be more users than R sessions involved with your app. So code that appears inside the server function will be run more often than code that appears outside of it, which means it'll take up more resources and your app will be slightly slower because it's doing more things. So if you don't need to run the code once each time for each user, put it outside of the server function. If you need to run that piece of code once for each user, put it inside the server function. And then finally, you'll be making outputs using render functions to make them. And the code inside of a render function gets run most often of all. Every time someone switches an input, that code will be rerun. It might be rerun 100 times a minute or so. So you should put the bare minimum code inside a render function that is necessary for updating that rendered output. So that's the first tip I have. Think about where you call the code in your Shiny app. And then the second tip is more abstract. If you're like me, I knew R pretty well before I started using Shiny, and it was a real stumbling block to me to imagine how Shiny was actually creating this reactivity, because based on what I thought I knew about R, I just thought, well, there's no way R can behave like Excel. That's not how R works. Well, you could search through the source code for Shiny and figure out and satisfy yourself that yes, it does work. The source code is pretty complicated, so I've written an article that explains it in easier to understand terms. This won't necessarily help you write better Shiny apps unless this is something that's been distracting you and making you wonder. So feel free to ignore this. It's just if you feel inquisitive. And then finally, if you want to learn anything about Shiny in the meantime, I encourage you to go to the Shiny Development Center at shiny.rstudio.com, where we have a gallery of example apps, a tutorial that you can take, and articles that cover deeper topics about Shiny. So thank you very much for your patience. I know this webinar ran slightly longer than last time, and I know it's definitely much more technical, but I think it is also more empowering. The things you can do with Shiny now are pretty impressive. You just need to assemble them in creative and sophisticated ways. So as Roger mentioned, this is the last webinar in the series, and we're going to cover the last component of Shiny apps, which is how to stylize the apps and customize their appearance. Just as before, I've put these slides online. In addition to being in the GitHub repository that we make for this webinar series, these slides will also be available from the short link bit.ly Shiny Quick Start 3. And just like in the last two webinars, we're going to look at some very basic Shiny apps. I'm trying to break it down as simple as possible to make it easy to learn the parts of Shiny separate from each other. But of course, when you put all this stuff together, you can make really sophisticated and impressive apps. And if you want to see what those apps look like, then I recommend stopping by the Shiny Showcase, whose link is right here. So again, this is the last webinar in the series. The other ones are available online, so if you haven't watched them before today, you can go back and see them later, and soon this one will join those as well at the same website. So here's what we covered so far, just a reminder of what we did in the past 2 weeks. In the very first week, we learned that a Shiny app has two parts. It's a web page that people can visit, but embedded in that web page are things they can manipulate and outputs of R analyses. And behind the web page is a server, a computer that's monitoring the web page with an open R session that's ready to run analysis in R whenever it needs to update that web page. And by working together, these things create an interactive web app. We learned how to share apps through shinyapps.io or to set up your own server, either the open source or professional version. We learned how to start building apps with a useful template that you can use over and over again. The first part of the template sets up the web page that your users will visit, and the second part sets up the server to manage that web page and create interactions. In the second webinar, we looked at all the ways you can control the reactions in your Shiny apps. Today we're going to look at the last component. That's to take your basic Shiny app, which looks like the app on the left, and manipulate the appearance so it looks like something more impressive, like any of these apps we see here on the right. And what we're going to do, what we're going to use to do that is the underlying HTML UI of a Shiny app. So we say in a lot of places that you don't need to know HTML to make Shiny apps, and that's true. And you'll see today that you don't necessarily even need to know HTML to use the stuff we talk about today. But of course, HTML does underlie everything that we do here because we are working with web pages. And the more you know about it, the easier you'll find it to navigate the appearance of your app. Now, I don't write web documents myself, but I do know HTML, I do know CSS. I just rarely have a chance to use it, so I often forget it. And what I found is that all these things are very well documented online, and you can search for anything on Google very easily. So recall that the user interface of your app that we've been making with Fluid Page is really just HTML. We use R functions to make it, but these R functions, if you ran Fluid Page at the command line, you'd see they're just returning HTML. We could pay attention to that HTML, or we could ignore it. It doesn't matter. We've seen before that you could, call Shiny functions to add inputs and outputs to your user interface, and those functions themselves, they're also just calling HTML or writing HTML. So this idea that you call R functions that return HTML to build the app is something we'll return to throughout the day. This is a basic paradigm for setting up the appearance of your Shiny app. You call an R function, and that function writes the HTML for you. So just realize that we're going to be calling R functions to work with HTML. Fluid Page is a quick way to set up a user interface for your app. And then we already know that you can use input and output functions to create the reactive components for your user interface. And then finally, you save that output to UI if you're using the template that I recommend you start with. So you know from the previous webinars how to set up reactive content in your user interface, but you can also add static content. This would just be purely visual content to your app. And we're going to look at how to do that. Now, since your app is a web page, we might start by considering how would you add content to a normal web page. And if this is our web page, we have a basic Fluid Page here. Looking at the HTML side of it, we might add a title to it by using the HTML tag h1. It makes a first level header. We could add a paragraph of text with the HTML tag p. It stands for paragraph. And inside that paragraph, we can nest another tag. A is the anchor tag, or it's the tag you use to make web links. When we do that, our app will have a web link on the side. And then if we wanted to stylize something, like if we wanted the text in our paragraph to be a little different, then inside that paragraph tag, we could add some style. We could add a style argument, or in HTML it's called an attribute. And here I'm just setting the font to the impact font. And so it changes how the font looks. So this is how you do it with HTML. You use these things called HTML tags. Well, we're not going to be writing HTML. We're going to be writing R. And in R, you call a function that recreates the HTML tag. And Shiny comes with something special. It's a list of functions that's saved under tags. So this tags object will be a list of functions. And then within that object, there's a function for every HTML tag that you could create with HTML. So if you know HTML, you can just map onto your knowledge that you already have. And if you don't know HTML, you could just learn with me right now the most common tag functions that you're likely to use. And then if you ever want further guidance about what to do, you could Google HTML tags to see what's out there. Or go to the Shiny Dev Center where I've written an article about all of this. So this tags object is a list, and it contains 110 elements for 110 different tags. We're just looking at the first 40 or so here. And you can see that each of the elements has the name of an HTML tag. For example, we see right away that A tag we looked at earlier. It makes a web link. It's a little unusual, this object, in that it's a list, which I'm sure we've all used in R before, but the elements of the list are themselves functions. That's completely permissible in R. Don't be worried about it. Don't let it distract you. If you were to look up one of the elements in the list using list syntax like tags $h1, it will return the same thing that would happen if you just typed in the name of a function R. Say you typed in the name of a function mean. You don't put parentheses behind it. R doesn't run the function. It shows you what code is inside the function. So here's the code that's inside the h1 function. I show you this because this is probably not really what you ever want to do, but it might happen. If you want to use one of these functions in the tags list, just refer to it the same way, but put parentheses after the function. This is how you trigger the code in a function to run when you use R. So now if I run tags $h1 with parentheses, it actually runs that function. And what that individual function does is it just inserts an h1 tag somewhere, not surprisingly. So these tags functions have their own syntax. They're all part of the tags object, so you have to find them there. In many cases, you couldn't write something like table, which is one of the tags, and expect to get the tags function that creates a table. R has its own function that does things related to tables, whose name is table. So you need to use the tags $ to specify that you're specifically talking about these Shiny functions that recreate HTML tags. Once you do that, you choose the name or the element of the list that you want to use. The name will correspond to the HTML tag that you're trying to make. So here I'm calling A, and that will make an H tag. By the way, this HTML at the bottom of the page is the output of the R code at the top of the page. Next, you could give the tag named arguments, and any named argument that you give to the function will appear as an attribute of the tag. So notice that href down below is in between the braces, or the less than sign and the greater than sign. This is where HTML attributes appear. When this A tag goes into your website, your viewer won't actually see www.rstudio.com. That's meta information that the tag uses. In this case, when the user clicks on RStudio, it will take them to the website, www.rstudio.com. So the way you add those attributes is you pass them to your tags function as a named argument. If you pass arguments to the tags function that do not have names, then the function will put it in between the tags or inside of the tags in the HTML. So here, when I write RStudio with no name, it becomes the text that goes inside the A tag. And for the A tag, that will be the text that your viewer sees and can click on. It will normally be blue or underlined, something that tells the viewer that's an active web link. Now, one thing that you could pass to a tags function is a second tags function. You can nest them together. And I have a slide that shows what that looks like. So how would you use these things? You could call the tags function inside Fluid Page in the UI of your app to start adding different tags. Here I'm adding 1st through 6th level headers using the functions h1 through h6, which all exist in the tags list. If you want to make a web link, you do that with the A tag, and every web link will need an href, that's the URL that the link will go to when you click on it, and then a piece of text to show as the link. You could write text without calling a tags function. If you just pass a character string to Fluid Page or any Shiny layout function, that text will appear right in your app. But if you want to organize the text into separate paragraphs, you could do that with the P tag. So now the same text has 2 paragraphs. And if you want to make italicized text, you could do that with the EM tag. It stands for emphasis. The strong tag makes bold text. The code tag makes text that looks like it's code. Depending on what sort of web browser or styling, we'll talk about that later, you're using, it may or may not show up pink like this, but it will look mono-spaced code-like text. And then you can nest tags together. So here's the P tag that makes a paragraph, and I'm actually passing it 3 unnamed arguments. They're all unnamed, so let's go knit them together to be the text that appears inside the P tag. But one of those arguments is a second call to tags. In this case, it's a call that makes some bold text that says Shiny. And you can see how this comes to appear in our app. We have a paragraph. One of those words is bold. The rest is, as you would expect. The BR tag inserts a line break. The HR tag inserts a horizontal rule. So if you'll look closely at the app, you'll see there's a slight gray line going across. That's what HR inserted. And then a popular thing to insert into web pages, certainly, and Shiny apps are images. And you can do that with the IMG tag. It's a little different than the other tags in that every argument needs to be named. It's very common to put a height and width in there in pixels, the height and width of your image. But then the essential argument with image is SRC. It stands for source, and that is a link to the file that actually contains the image that will appear there. You could set source to a URL if that URL contains an image, like if it links to a PNG or a JPEG or whatnot, if you go to this URL, you will actually see, I'm pretty certain, this this RORB, although don't take my word for that. More commonly, instead of linking to an image that's already online, you might link to an image that you yourself own and have on your computer. If you want that image to go inside your Shiny app, then there's a special way to include it with your app. Inside of the app directory folder, whatever you've named the directory that contains your app.r file, and the other files, make a folder called www. Use that name specifically. Shiny and Shiny servers, when they deploy your app, all of the files that appear in the www folder, the server will make accessible to your user's web browser. And so your web browser is what's going to assemble the app on their end. And if you want an image to appear in the app, the web browser is going to need a copy of that image. Later on, when we work with CSS, we'll need a copy of the CSS files and whatnot. So the first thing you want to do when you want to share an image to include in your app is make a www folder and put it in that folder. And then once you've done that, you can just use the file name of that image as the source argument for that image to appear in the app. Now, one thing you'll notice if you download the course materials today, and the link's at the top of the slide right here, you have a PDF copy of all these slides, but in there, there's also, I'll show you. When you first download it, it'll look like this. You'll have the PDF slides in the code folder. And inside the code folder are many examples that parallel what we're talking about today. We have an example of making a Shiny app with just pure HTML. So you can open that in the editor. We have a Shiny app that creates that HTML using the Shiny tags here. And then we have this app directory. And what app directory is it's basically the directory I showed in the last slide. We have a script here for an app. And this app uses an image. This image is called bigorb.png. It has a www folder, and in that folder is that image. So you can see this is how we would include an image in this app. And if I were to run this app, you'll see it doesn't do anything really, but it does contain this image that was in the www folder. Also notice you don't need to put www/ in front of the image. Source will look for it right in the www folder. If you have a subdirectory inside that folder, then you would put the subdirectory name. Think of this as a file path that goes from www to your image.
So all of these functions are available in the tags list, which means you could call them with tags $, and then the function name. But for the most useful functions, and the ones that don't conflict with our names, or the names of functions that already exist in R, we've gone ahead and made wrapper functions that you can use to access the function in the tags list.
And for example, h1 is a function that comes with Shiny. It's a wrapper for tags $h1. And it's just a way to save you typing. You could call h1 instead of tags $h1. You can see right here in the code, it's just going to call that for you. And so when you're working with the most common tag functions, you could resist writing tags. Now, there's no real rhyme or reason which ones have wrapper functions, which ones don't. It depends on what already existed in R and whatnot. So tags will always work, and then you'll find through experimentation you don't need to call it all the time. So these are probably the most common, the most useful tags functions. They all have helper functions or wrapper functions, so you don't need to call tags in front of these ones. And they're just the ones we went over in the slides. So here's the app I showed you before. And if you go to RStudio and you actually took this code and saved it in the RStudio IDE, then you'd have basically what we have up here in the first file, tags. Look at it over here. One cool thing about the RStudio IDE is that if you have an HTML file and you have HTML in it, you save it with the extension.html. RStudio knows it's HTML, and it will actually preview the HTML for you. So if we want to see what this code looks like in a real web page, we could just click preview, and there it is. This web page isn't that fancy, but this is really useful if you like working with HTML. Going back to the slides, we could recreate everything that's here just using the Shiny tags functions, and this is the paradigm that you use with Shiny. So, instead of writing div, we could call fluid page. We could call h1 to make that h1 header. Now, one thing is, since this is R now, when we want to pass that text H1, we put quotation marks around it. You can see here with the HTML, that's not a consideration, but that's okay. To make that paragraph, we could call the P tag. We could call the A tag to make the link. And then when we're done, our web page will look like this. You'll notice it's a little different, and that's just because, well, frankly, the previous version was kind of ugly, and Shiny comes with some basic styling that tries to make everything pleasant looking. But you can see we're still using the fonts we asked to use, and we still have our links and our headers and everything we asked for. And then, of course, we could do all this using the tags syntax to access those functions as well. And then there's one other way we could go about this. This is all HTML here. It's legitimate HTML. And you could pass HTML straight into a Shiny app, and then Shiny will use it to build the web page. The way you do that, perhaps I shouldn't say straight into the Shiny app, is you pass it to a function called HTML. So first, make it a character string. Here I'm using a single quotation mark to make this a character string. And then passing it to the HTML function. And then Shiny will parse that as HTML. We've told it through the function that this is actually HTML. It's not text we want to appear in the app. And then we'll end up with the app we see here on the left. So the way that HTML function works is you just call it, it's all capitals, you give it a character string that contains raw HTML, and then Shiny will interpret that string as raw HTML and put the results into your UI. All right, so let's recap what we've learned there. You add elements with the tags functions. They appear in the list called tags, and you access them with list syntax, tags $. For each of these tags functions, it will take unnamed arguments and pass them through inside the tags. It will take named arguments and pass them as HTML attributes. So if you want to know which named arguments you could use for a given tag, just look up that HTML tag and see which attributes it works with. And then finally, you could add raw HTML with the HTML function. Now at this point, some of you, perhaps 60% of you based on that poll, will say, hey, I already know how to use HTML. Why do I need to relearn how to recreate it with R? Can I just make my UI from HTML? And the short answer is yes. This slide is for you. It links to an article that explains how to just start with an HTML document and to add the Shiny components of that, so you don't have to write the UI in R. That said, however, even if you know HTML, I recommend that you use these R functions, or at least try them out and give yourself a chance to get comfortable with them. Because I think it's easier in the beginning to stick with one language, R, since you have to write R for the back side of the app anyways, than to go between two different languages. But of course you have your freedom here to do what you prefer. So the other thing that web documents do, or HTML does, besides adding elements to a web page, is it lays out those elements. And that's not something we've really looked at yet in our Shiny apps, but it's certainly something you can do. Picture this gray box here as being your Shiny app, and we want to put this slider into it. Well, you have the freedom to place that slider anywhere you want in your app based on a grid that has, an X dimension. So you could place the slider on one side, move it to a different place. And we can also move it up and down in the app based on the Y dimension. So we have a little bit of freedom of where we place our elements. And then if you think of the app in 3 dimensions, so for example, we might stack some elements on top of each other. You can only ever see the top one, but you might be able to change which ones are on top. Then you could also think of your app as having a Z dimension, and you can determine where in the app to place your elements on the Z dimension. The way we're going to do this is with some functions that also create HTML, and they exist purely to create layout for your app. So these functions return divs, an HTML division, and the divs are set up in a way that it breaks your app into separate dividing spaces, and then you decide which space to put your elements into. And the 2 main functions are fluid row and column. So let's take a look at those. Fluid row will divide your app up into rows. So this is like a horizontal strip, and you could add as many as you want. Every time you call fluid row, it'll add a new row to your app, and the new row will appear below the rows that are already there. So this UI code over here would divide your app up like this. Now you won't see boxes with blue dash marks and the words row 1, row 2. This will be invisible divisions. but I want you to see how it gets divided up, so that's why those are there. The fluid row functions work together with the column functions to create a space to place each of your elements. You could pass an element straight into fluid row. To be honest, on its own, fluid row doesn't really do much. If you don't use fluid row, R is going to stick your elements in there one on top of each other, and if you do use fluid row, it does the same thing. But when you add column to fluid row, now you have a complete system. What column does is it creates a space inside of a row that has a certain width, and then you could place your apps inside the width. So for example, here I'm calling 3 different columns and 2 different rows. The first argument of every column is a width. Every column has a certain width in units, and the way those widths work is based on a base 12 system. So no matter how wide your app is, the row is considered to be 12 units wide. And the width argument of a column determines how many of those 12 units you want the column to take up. So in the top row here, we have one column that takes up 3 of those 12 units. And then the next column will be inserted right next to it, and it will take up 5 of those 12 units. So you can't have a column that's more than 12 units, obviously, and I've never tried it. It just occurred to me you could try it, but I don't think you can have a column less than 1 unit either. That wouldn't make any sense. As the breadth of the window changes, the width of those columns will change relative to the window fluidly. That's why everything says fluid over here in the UI. The second argument that a column can take is an offset argument, and that inserts a number of units between the left-hand side of the page or the end of the previous column before this column starts. So this last call to column here offsets that column by 8 units, pushing it all the way over to the edge of the page. Again, you won't see any of these blue dots or blue areas in your app. All these divisions will be invisible until you start putting things into them. But now we've created this setup, let's look at how we can use it to put elements into our app. And then also, just remind yourself, these things are just writing the HTML for us. This is just working the way HTML normally works. All right. If you want to put something into a row, then you could just pass it as text to fluid row, and it'll appear inside that div, which means it'll go wherever that div is in the app. If you want to put something inside a column, then just pass it as an argument to column, and it will appear inside the div that makes that column. So this second div in the blue down here, that's the output of plot output, just to remind you. So it's putting whatever plot output outputs into the div that goes along with that column we created. So if we go back to the layout that we made, we could put a slider input, just gloss over the arguments for slider input, into our second column there by passing it as an argument to the second column function, and that's where the slider input will appear in our app. We could put a histogram into the third column just by passing it as a new argument to that column, and it will appear over there in that column. And when we're done, our app will look like this. Not really that impressive, kind of samey, but this is the system that you would use to place things where you want them in your app. And you could pass more than one thing into a column. You could pass more than one thing into a fluid row. R will just stack them on top of each other and fit them where you've asked them to be. They'll share that space. Fluid rows will expand their height to accommodate whatever happens to be inside them, and pretty much the same for columns. So let's recap that system. You could position your elements in a grid in your app, or you could stack them on top of each other in layers. So that's how you lay out your app. We haven't looked at layers yet, but we'll get to that. Use fluid row to range elements in rows. Use columns to range elements in columns. And then you can position columns where you want them in your app along those rows with the width and offset arguments. The width argument is mandatory. You have to use that. The offset argument is optional. So now let's look at how to stack those layers of panels into your app. That'd be the Z dimension I talked about earlier. So panels are a thing in Shiny. They're the basic unit of grouping together elements. And when you group elements together into a panel, then they act as a single element for you to place in your app. And usually that panel element will have some unique properties of its own. So for example, what we see here is a title action button, a button called action, a horizontal rule, some text, some display, and another button that have all been grouped together as a single element into this panel. In this case, it's a well panel. And if you visit that link, you'll see there's an app here that sort of demonstrates all the different input objects you can use in Shiny, and it relies heavily on grouping things into these well panels. So a well panel is an example of a panel. The way you create one is with this function well panel, and this code I'm showing you is one of the example codes that's over in the code folder. This is how our app looks without a well panel. If we just surround the two inputs at the top of the app with well panel, then it places them together in this gray well, which visually works very nice. It's a visual way to group things together. Shiny contains 12 functions that make different sorts of panels. Each of these group objects together, and they do something a little different with the objects. I'll let you explore these at your leisure, but we'll look at 3 of these very closely, and we'll look at some of the other ones later, because 3 of these are involved with stacking panels on top of each other. If you want to start stacking things on top of each other, then you begin with tab panel. It creates a stackable layer of elements, and inside that tab panel you can put whatever you want. It's like a small UI of its own. So you could add fluid rows and columns inside there to lay it out, or you could just drop an element in there like a graph. Every tab panel needs a title because when you start stacking panels on top of each other, you need to be able to navigate between them, and the titles go to be an essential component of that navigation system. And then after you give it a title, you can give it whatever elements you want to appear in that panel. Tab panels are designed to work with one of the following functions: tab set panel, navlist panel, or navbar page. We'll look at the 2 panel functions first, and then we'll look at the page function in the next module. What tab set panel does is it combines several different panels together in a way that you can navigate with tabs at the top of the panel. So here you see we've called tab panel 3 times, and we've given each of our panels a title, tab 1, tab 2, tab 3. We've put them together with tab set panel. In the app, you can see the titles of each of those tabs, and you can click on the tabs to actually navigate to what's in that part of the app. So there's a navigation section here to the stack, and then there's a content section. And we'll see that with navlist panel as well. If you wanted to think of our imagery here, each of these slices, each of these layers is a tab panel, and then this stack of layers is what I'm calling a tab set panel. Before we look at navlist panel, let's go over to RStudio and look at our example of a tab set panel, because I think that will really make it easier to understand. O5 Tabs is an app that it does some stuff. So I had to write some code to make this sophisticated. We don't have to go through the code, but based on the past 2 webinars, you'd be able to understand it. However, notice it is grouping things together into tab panels. We have 3 of them. And it's grouping those tab panels into a single tab set panel. So if I copy all this code and run it at the command line, it'll launch this app. Then the app looks like this. It's just showing some normal data here. I could take a new sample of normal data. And you could use it to get a feel for how normal data actually looks when you only sample 500 objects. But this is just the top layer of the stack. There's 2 more layers behind it. And if I click on one of those, I could see that this layer, now it's at the top. It's doing the same thing, but it's doing it for uniform data. And then the final layer does it for chi-square data. Each of these layers has its own resample button. It looks like the button's not changing, but don't be fooled by that. It's just each layer has the same button in the same place. So this is how a tab set looks in practice. It's a convenient way to put a lot of things into a small amount of real estate. And then the navlist panel does a similar thing. Use it just like tab set panel, except you call navlist panel instead of tab set panel. You pass to it tab panels, and then it will display a sidebar of links next to the contents. So its navigation is a sidebar. It appears next to the contents if there's space for it. If there's not space for it, it'll move to the top of the contents, and then the contents will appear there. In all other respects, it works the same way as tab panel. And then there's an example of that there too, and we could take a look at that. That, of course, is O6 navlist. Let's run this one. And here's our same setup, but now we navigate through the sidebar. All right, so what should you know about panels? Panels are a common way to group elements into a single unit for reasons that could be functional when you're making a stack, for example, or just purely aesthetic like well panel was working. You use tab panels to create stackable panels, and then you put those panels together into a navigable stack with tab set panel or nav list panel. Now these things, as well as the row system and the column system, are all documented in this article here. So if you would prefer to go through this at your own pace, reading about it and seeing examples in code, visit this article. And then, in addition to building your layout with the basics that we just covered, Shiny does come with several pre-packaged layouts that can save you time if you want to do what they already do. And what I'd like to do is go over those for you. Probably the most common way to build a Shiny app is with a sidebar layout. And there is a layout function called sidebar layout that works together with two of these panels, sidebar panel and main panel, to divide an app into two sections, a sidebar and whatnot. The way you use it is you put the function inside fluid page, and it only takes two arguments, and those arguments must be the output of sidebar panel and main panel. Well, those are the two required arguments. There are other arguments you can find on the help page. And then when you want to put something in the sidebar, just pass it as an argument to sidebar panel. And if you want to put something in the main panel, pass it as an argument to main panel. And we do have an example of that in the slides or in the code. And if you've seen any Shiny apps whatsoever, you've probably seen an example of sidebar. So here's the sidebar. It only extends as far down as it needs to based on what you put in there. And then here's the main panel. I've put my plot there. Since this is a fluid page, the sidebar won't always stay on the side. If I make the page completely narrow, instead of trying to wedge both things in next to each other, Shiny will put the sidebar back on. We'll put it on top here. But technically, it's still a sidebar. Another approach to laying out a Shiny app is to use fixed page instead of fluid page. So you notice that our apps have responded as we change the width of our browser window. And that's because we're using fluid page. The whole point of fluid page is to respond fluidly to the dimensions of the browser window. Fixed page does not do that. It will create an app that's either 724 pixels wide, 940 pixels wide, or 1170 pixels wide, based on whatever the current width of the browser window is. So you could change the width of the window, but the dimensions of things in the app won't change so much until they make one of these jumps. Use it with fixed row instead of fluid row, not too surprisingly. And I find that I've never had a reason to use this, but it is there. In general, you'll probably stick with fluid page. And then something that you likely will use quite a bit is navbar page. So navbar page sort of picks up this idea of stacking panels on top of each other. It takes a title, it always needs a title, and then it takes three panels. Well, let me take that back. It takes as many panels as you want to give it. In this example, I'm using 3. Navbar page replaces fluid page. So if you were to use navbar page, you wouldn't call fluid page, you just call navbar page. And then you give it its title. And what it will do is it'll take the tab panels that you give it and assemble them into a single page that has this sort of navbar at the top of the page. You'll see your title. That title will appear all the time on the app. And then you'll see the different titles of the tabs. When you click on one of those tabs, you'll go to that place. So just like before, we get to give the navigation and the contents. But in this case, the whole page will be the contents. With tab set panel, you could conceivably just put a tab set panel in the sidebar or in a main panel or just some portion of your app. But with navbar page, the entire app is the stack. It gives the appearance that your single app is a set of multiple web pages that the user can navigate back and forth with. And if we go back to our code folder, there's an example there which shows this off very well. Let's take a look at it. It is the navbar page example. And you'll notice I'm using navbar page instead of fluid page, giving it a title. And then this is the same code as in the other app. I'm using the same tab panels and whatnot. When I run this, we get our resampling app. But now I can move between the different pieces of code up here. The next example shows off what we're going to cover in the next slide, so let's just take a look at it, because I should be better about naming these things at the top of the file. It's again calling navbar page, and it's again calling tab panels. But I'm using a helper function here, tab menu, or navbar menu. So one tab panel is directly under navbar page, but the next two tab panels are under navbar menu. And I've given the menu a title itself. If I run this code, I get almost the same map, but you'll notice that the navbar appears a little different. Instead of having normal data, uniform data, chi-square data, I have normal data and then other data, which, if you'll remember, was the title of my navbar menu. And then when I click on other data, I get a drop-down menu with the titles of the remaining two tabs. So navbar menu is a helper function that helps you put even more tabs into a single navbar. Come back to the slides, we could take a look at how that works. You could put tabs either straight into the navbar page, or you could put them in the navbar menu. If you put them into the menu, they'll show up under the title of the menu as a drop-down menu. And then finally, there's a very aesthetically pleasing prepackaged layout for you called dashboard page that doesn't come in the Shiny package, but it comes in the Shiny dashboards package. And the Shiny dashboards package contains other functions that help you create a dashboard-like layout, and even inputs and outputs that work best with the dashboard layout and don't come with the regular Shiny package. You could take a tutorial about Shiny dashboards at the link at the top of the page here, and then Winston Chang, the author of Shiny Dashboards and the maintainer of Shiny, filmed his own webcast about the Shiny Dashboards package just last month. So you could check that webcast out at the link below, and it's titled Dynamic Dashboards with Shiny, the webinar. All right, so when it comes to prepackaged layouts, you can use sidebar layout to quickly create a side panel and a main panel. You can use a fixed panel along with fixed row to create a non-fluid Shiny app. And then you can use navbar page, perhaps with navbar menu, to create a multi-page app like the ones we were looking at. And then finally, the Shiny dashboard package provides an additional layout for creating administrative dashboards with Shiny. All right, so now we've looked at how to add static visual elements to your app, how to lay out those elements, but we haven't really looked at how you could change what these things look like once they're there. And that's what we'll look at last before we leave. And the way we'll go about this is with CSS. So what is CSS? You may or may not know that every web page you make is basically just a simple document that looks like the thing on the left here. In fact, if you have a very slow internet connection, you visit your favorite web page, you might have been surprised once or twice to find out that it looks really bad. I mean, everything's there, but it doesn't look visually pleasant at all. And that's because you're seeing the page without the CSS styling. CSS is a way to take the basic elements of an HTML app and tell your browser how they should look. So instead of displaying a piece of text, display text that is blue and uses this font and is this size. All those extra elements to the text are called CSS. And for example, if you went to Shiny Dev Center, you'd see the web page that you see here on the right, hopefully, and it's built off this web page on the left. This is what the web page looks like with no CSS. I use CSS to turn the basic elements into what we see at the end of the day. And since Shiny apps are web pages, the same approach applies to Shiny apps. Let's go over to the code and look at this stuff live. So the last example, css.html, is an HTML file that creates something when you preview it. Creates this web page. So this isn't a very spectacular web page, and actually it's very text heavy, especially for a webcast. But it's self-explanatory, so you could look at it later when you're not in the webcast. And what you'll see is, it's a web page with a title, has some text in here, and already the web page looks a little more pleasant than what you get with the basic web page, where things would be, some sort of serif font. Don't really know why for a computer, but this one is sans serif, and the colors are pleasing. And then the actual colors down here are alternating between these different shades of blue and purple and green. If we look at the code that makes this, you'll see the web page starts with a header section. So between these two tags that say head, it's a header section. And the first thing in the header section is a link, or a tag that says link, that links to a CSS text file. It's a style sheet. And the name of the file is bootswatch cerulean.css. So this is a CSS theme that's free online from the Bootswatch project. Its name is Cerulean. Download a copy of this to my computer, which we could actually see over here. There it is. And I'm telling the web page to use that CSS to style whatever comes out of here. If I were to delete that, re-preview the web page, you'll notice everything goes back to sort of Times New Roman or whatnot. So this, by linking into the CSS file, I'm setting the CSS for the web page to go along with everything that's in that file. If we actually look at that file, you can see that it's not really that readable, but it contains a lot of styling in here. And all of this is being applied to our web page. Let's close that. Next, there's a style section, and in the style section, there's some code. This is what CSS looks like. This is saying take any tag that's an li tag and make the text purple. Take any tag that has the class blue item and make that text blue. Take any tag that has the ID dark and make that color navy. So it's very simple CSS, but you'll see there's some notation like this dot here and this hashtag. That's part of the CSS language. We could look at that further down here. Right. So here's the first paragraph we see, the paragraph that's gray here. It just explains that we're using the basic CSS for this article. There's nothing here that talks about p tags, so this is just straight up CSS, or it's straight up text, and if it's using any CSS, it's using the CSS provided by this link. Down here we're making a list. OL is the HTML tag to make an order list with these numbers here. And each of the entries are what appears between these li tags. It stands for list item. The first list item is just using the regular CSS, well, it's using the global CSS we've written up here. Notice I've asked list items to be purple, and this list item is purple. The second list item is not purple, it's blue. And if we read it, it would say that we're using the class-based CSS, the CSS for items of class blue item. Up here we ask them to be blue, and this one is becoming blue because we've set it to this class. In HTML, you set the class of a tag object by giving it the attribute class. The next one has the class attribute. It also has an ID attribute, attribute dark. You can see up here there is some CSS associated with the ID dark, so that CSS is being applied to this link, so it says navy, dark blue. You notice that this CSS is overriding the class-based CSS, which would make it this color, and it's overriding the list-based CSS, which would make it purple, and it's overriding the CSS we linked in way up here, which would make it gray. So we're seeing that there's a bit of a hierarchy here. We'll take a look at that in the slides. And then finally, the last one also has an ID. It also has a class, but it has style written right into the tag here. This style is CSS. And if you write style straight into a tag, that will overrule everything. We ask the type this item be green, so there it is, it's green. What does all that mean? Well, that's certainly a mouthful, and that's a lot to take in if you've not used CSS. I don't expect you to get CSS out of this webinar. There's certainly no time. There's barely time to cover what's left. But the big themes you can use to guide you as you style Shiny apps. So you style a web page in 3 ways. You could link to an external CSS file. You could write global CSS in the header under this, in between the style tags, or you could write individual CSS in a tag style attribute. So for example, when I said style equals color green. And then you could have CSS apply to things in different ways. You could write CSS that applies to every tag, like every li tag. You could write CSS that applies to every class, start giving things classes. You'll notice that a lot of the things in Shiny have special classes, and each of those classes are just a collection of CSS that makes that thing appear in a certain way. And then finally, you could give individual tags IDs and have CSS match up to the IDs. In each case, the items at the bottom, if they have CSS, they'll overwrite any CSS that's inherited from above. Same on this side. And this is where the cascading with cascading style sheets comes into play. You could use one of these first level things to create global CSS, and then you can manipulate things on top of the global CSS by applying CSS in one of the second or third places. Shiny uses the Bootstrap 3 CSS framework. You could learn about this framework and see it online. It's very popular. You've probably seen it in other places. If you go to this link, you can find out even more about it. but it's useful to know that Shiny CSS is coming ultimately from the Bootstrap 3 CSS framework, which means if you look at something like the output of fluid page and you see that's class container-fluid, well, that is a Bootstrap class that has a bunch of CSS associated with it. If you wanted to know about that CSS, maybe manipulate some of it, go to the Bootstrap 3 CSS framework, look up that class, search through the documentation, see what's going on there and what you can change or not change. Next, you can style a Shiny app the same way you style a web page, because of course it is a web page. You could link to an external CSS file, you could write global CSS, and you could write individual CSS. And these things will override each other in the appropriate way. Now, as you write CSS, it makes sense to write CSS that will work with the Bootstrap 3 framework, because the things you don't change will still use the Bootstrap 3 framework. All right. If you want to link to an external CSS file, you should put it in the same folder you put your images I mentioned earlier, the www folder. The browsers that your users have will need this file to create the web page just the way you want it to be. So put it in the www folder and Shiny Server will pass on these files to the browser for them to use. Once you've done that, if you're using Fluid Page and you want to have your whole app use that CSS file, you could set the theme argument to the name of that file. So for example, if I put bootswatch-cerulean in my www folder, then I could set the theme of the app to the name of that file and it would use all of that stuff. There's also a second way to do this. You could use the tags $head and tags $link functions. The tags $head function creates a header section for your app. Remember, the head section is where all the CSS appeared in the real web page we just looked at. Inside of tags $head, everything you put there will appear inside the header section of your web page. If you wanted to link to a CSS style sheet, then you can use tags $link to do that. Give it the 3 named arguments that style sheet uses, and then that link will be inserted into the header of your web page, and that CSS will be used. All right. The next way to include CSS is to just write some global CSS in the header. You can do that the same way. In this case, that CSS should appear between style tags. So inside tags $head, call tags $style. And then you don't want to pass that CSS in as a character string from R. You want to pass it in as HTML. So wrap what you give to tags $style with the HTML function. You could do the same thing, cutting out the tags head and tag style by just calling include CSS on a file of CSS. Now that CSS will have to already be written and saved in that file. That file should be in your app directory. It doesn't need to be in www, because what Shiny's going to do is it's going to read that file and just go copy and paste everything from that file straight into the header section. So the CSS will travel around with the web page. It will be there in the head section. That's the include CSS function. And then finally, you could write individual CSS in your tags style attributes, which we've been doing before. We just didn't call it CSS. It was CSS. If you want to make an H1 header that is red, you could set its style attribute to color :red, which is the CSS to make it red. So if you don't know CSS, I doubt you feel more confident about it coming out of that quick lesson. But there's a free tutorial online that I do recommend. We're not affiliated with Codecademy, but I've taken the tutorial. I think it does a good job of explaining the basics of CSS and HTML. And since both these things underlie your Shiny app, they guide the way that you change the appearance of your Shiny app. This would be a good place to brush up on those things, especially if you've never used them before. They are not hard to learn. If you were making Shiny apps, you can handle HTML and CSS, but they are tedious to learn, so this tutorial does help. Finally, I've written an article about adding CSS and other things to your app. It's linked here. It goes into it at a little slower pace and it's more detailed. And I recommend you check this out if you're interested. And then also, the things we're doing with CSS are very similar to what you would do if you wanted to add JavaScript to your Shiny app, which you can do. You put a JavaScript into the head of your app or the footer. And this article goes through an example of adding Google Analytics to your Shiny app using jQuery, which is a way to add JavaScript. So that's interesting to look at too. So let's just wrap up. I know we're almost done with time here. Basically, you could add CSS the same way you do it with HTML, but use your Shiny functions to do it. And if you want to look up Shiny's native CSS, look at Bootstrap 3. So now you know how to add static elements to your apps, how to lay out the elements, and how to style the elements once they're there in your apps. If you put this together with the other webinars, you know everything you need to know to build Shiny apps. You can build and share your apps, you can control the reactions, and you can now style the apps so they look the way you imagine them to look in your head. Where should you go from here? Start building your own apps. From here on out, the quickest way to learn is to just experiment and try it out. So build your own apps, share them, get them to work, ask questions. There's a Shiny tag on Stack Overflow, and there's a Shiny Google group you can find on Google. And then, of course, if you need any extra help, the Shiny Development Center is the place to go. There's a second tutorial there. There's articles, galleries, example apps, and all sorts of things to help you along the way.